Okay, welcome back to CE 28. So we are picking up that linear programming problem, linear optimization problem, where we have to maximize the amount of roadway maintained. And we have two sets of technology. And we are deciding on how much of technology 1 and how much of technology 2 should we use. And it figures that tech 1, the technology 1, tech 1 can maintain 3 miles of road per day, and then tech 2 can maintain 2 miles per day. Okay, so, and then we said we are trying to decide how much of X1 and X2 we should deploy. Okay, so our objective function, if you recall from last class, was 3 times X1 plus 2 times X2. Does that make sense? And because I'm using Google Doc here, so I can format it to be subscript. Oops. Okay, so this is our objective function, 3x1 plus 2x2. And what do we want to do to it? We want to maximize this 3x1 plus 2x2. And where x1 is the amount of crews assigned using technology 1, or the units of technology 1 used. And then we were given these 2 slides, and we were trying to write the constraint. If you look at the left-hand side of this, so technology 1 employs 1 supervisor, 6 laborers, 2 pickup trucks, 1 grading machine, and 2 rollers. Okay. And technology 2 deploys 1 supervisor, 15 laborers, 3 pickup trucks, no grading machine, no rollers, and miscellaneous hand tools. And then all of these combinations yield, you can maintain 2 miles of road per day. Now, if you think about this, we were going to write some constraints based on this. We're going to have to write some constraint based on this because the amount of resources available are fixed. So we have maximum of laborers. So let me create a table here. Okay. So I'm going to write the constraints here, and then we'll try to see if we can. So we have 150 laborers. So technology 1, we know. So the critical ones, I'm only putting in the critical ones. Oops. That's okay. So it uses 1 supervisor, 6 laborers, 2 pickup trucks, 1 grading machine, and 2 rollers. So this is a technology number 1. And then tech number 2 employs 1 supervisor, 15 laborers, and 3 pickup trucks, no grading machine, and no rollers. Okay. No grading machine and no rollers. And then you're given, then you're also given the total number of supervisors that you need. So you're given some constraints, and on the supervisor side, the constraints is that you need to have minimum of 6. And then we said, okay, one supervisor, and you need to have minimum of 6 supervisors. Then you need to have 15 laborers and 6 laborers. So, and for the laborers, you have max 150. So this is your constraint. You have max 150. You cannot employ more than 150 laborers. I'm going to just do bullet points here. And then for the pickup trucks, max of 40. So you can only have 40 pickup trucks. In terms of grading machine, you can only have 30 rollers and 10 graders. So max 10 graders. Okay. And then in terms of rollers, you can have max of 30 rollers. And what you can do now, and I can just reduce the font size here. I can take these things, and because I know that both technologies utilize one supervisor each. So if you deploy 1 unit of technology 1, you will be using 1 supervisor. So now you can start writing these equations in terms of x1 and x2 that look like your constraint equation. Okay, so your constraint equation would be, for the first one, 1 supervisor each, and you need minimum of 6. So I can say my equation will be x1 plus x2 So remember, this is minimum of 6. Should be greater than or equal to 6. Does that make sense? So this is my sort of like my supervisor constraint. And I can write it in the. Does that constraint make sense? X1 plus X2 has to be greater than 6. Okay. Can we take a minute to write here the laborer constraint? The equation for laborer constraint. What would that equation look like? Why don't you take a minute to write it down? I'll pause the recording. Okay. So because we have maximum of 150 laborers and technology 1 uses 6 laborers and technology 2 uses 15 laborers, I end up with 6x1 plus 15x2 must be less than or equal to 150. And then I wrote the pickup constraint because technology 1 uses 2 pickup trucks. So then if you're using x1 units of technology 1, the total trucks used will be 2 times x1 plus 3 pickup trucks for technology 2. So 3 times x2 must be less than or equal to 40. Now the question is, how do we write the grading constraint? Technology 1 uses 1 grading machine. Technology 2 uses no grading machine. And I can only have 10 graders at the most. I cannot have more than 10 graders. So what would that look like? Okay, so I've been recording this. So because in the grader and the roller, they don't figure in technology 2. So there is no coefficient for technology 2 when you write those constraints. Just simply x1 has to be less than or equal to 10 and 2 times x1 has to be less than or equal to 30. So now you've written all your constraint equations. There were no, because hand tools are unlimited in our problem. It doesn't matter. So we don't have to write the constraint for that. So this is what the equation looks like, 2x1 less than or equal to 30. Now the question for you is, if you look at all these constraints, one of these constraints actually does not matter. Which constraint does not matter at all? Which of these constraints doesn't matter? So the response that I got was the roller constraint doesn't matter, which is the correct response. Because if you think about it, if 2 times x1 is less than or equal to 30, then x1 is less than or equal to 15. But x1 already has to be less than 10 because of the greater constraint. So then I don't have to worry about, even if I include it or not include it, my answer, when I try to maximize my objective function, would not matter. It would not change. Okay, so I'll just stick with x1 less than or equal to 10. And that becomes my greater constraint. Now I could include this in the answer or not include the last one. It wouldn't matter. It wouldn't change a thing. But now I hope you understood the process of writing these constraints. Now the question is, if I try to write these constraints out, and I have them written out in my slides. Okay, 6x1 plus 15x2 less than 150, and the pickups and the graders and all that. And the order is sort of flipped here, but don't worry about it. And then for all linear programming problems, we assume that the x1 or x2 will both be greater than or equal to 0. So we're only talking about positive values of x1 and x2. Okay, that's always the case. Okay, so now what we do is we figure out what is the feasible region. What is the feasible region for this linear programming problem? Again, we are not going to do this for every problem. This is just for the demonstration purposes. What I'm showing you is each of these constraints drawn in, each of these constraints drawn in for labor, it's the blue line. So if you look at the equation of the blue line, it's 6x1 plus 15x2. 6x1 plus 15x2 less than or equal to 150. Okay, so that's this equation, this blue line. And then I point the arrows downward because the labor has to be less than 150, right? So if you go above that line, you'll be at more than 150. So that line sort of defines the constraint. For the pickups, the constraint is the purple line. And then your constraint is to the left of this. And that's the equation. The equation of the purple line is 2x1 plus 3x2 less than or equal to 40. So this purple line defines 2x1 plus 3x2 equal to 40. So I'm gonna try to write these down. So the equation of the purple line is, I'll go back to the previous slide real quick. It's oops. Okay, give me 1 second here. Okay. All right, so let's see. This is what my equations look like. So I can start to draw out slide, and I'm going to make this bigger. So what I'm going to do now is I'm going to try to put in all these equations. Obviously, this line is immaterial line, and that's basically x1 less than or equal to 15. And that's your roller constraint, right? Because I divided by 2 on both sides. Okay, so that wouldn't matter. This line is x1 less than or equal to 10. So this is your greater constraint. And then obviously the arrow that I'm pointing to the left means x1 has to be less than or equal to 10. So these lines are defining your equalities, and then the arrows are essentially pointing to the left if it's less than or equal to constraint, or to the right if it's greater than or equal to constraint. Okay, so let's think about this. This orange line here is the supervisor constraint. So the equation of the orange line is x1 plus x2 equal to 6. X1 plus x2 equal to 6, and my feasible region, and I'm going to point upward because my supervisor have to be more than 6. Okay, that might be some sort of a regulation. So I got this, and then this purple line is the pickup line. Pickup line is, or pickup constraint is 2x1 plus 3x2 less than or equal to 40. So this is the line 2x1 plus 3x2 equal to 40. And then I'm defining it inwards. That means it's telling me that it has to be lower than 40. And then I do the same thing for the labor. And I do it and that. And then if I look at the region, I have to find the region where all of these constraints are satisfied. So this shaded area is what I call my feasible region. And this feasible region, is it a convex region or not? That's the question. Is this feasible region that I'm defining by shade, is this a convex region or not? Yes or no? I'll take you back. I'll take you back real quick. What the convex region looks like, what's the definition of convex region is. Okay, convex region is a region where if you connect two boundary points, you don't have to go out of the region. For linear programming solutions to exist, that has to be the case. In the feasible region, has to be a convex region. The question is it a feasible region? I mean, is it a convex region? It is, right? Because you can take any. It looks like it is a convex region because if I point any line on the boundary of this region, I don't have to go out of the region to connect those 2 points. So if I pick any 2 points, for example, if I pick any 2 points, like for example, one here and one here, I can connect them without any problem, without having to go out. I can connect these 2 points. I can pick out any 2 points on this feasible region and connect them with a straight line without going out of the region. So that means I have what we call a convex region. Let's look at the next slide here. And then I'm going to start looking at drawing 3x1 plus 2x2 lines at different values of z. Okay? So I'm going to start with a lower value of z. And essentially these things, you can think of these as isoquants. So on all of these lines, they have the same slope. So that means the coefficient of x1 and x2 are the same. 3x1 plus 2x2. So this is a very low value for 3x1 and 2x2. Okay. 3x1 and 2x2. And then this is another value for 3x1 and 2x2. Okay. So here I'm maintaining 6 miles of road. Okay, along this line, I'm going to always be able to maintain 6 miles of road. Oh, sorry, 12 miles of road. I'm sorry, 12 miles of road along this line. Along this line, I will always be able to maintain 24 miles of road. Okay. And then this number keeps going up and up as I move right. I'm able to maintain more and more amount of road. And the optimal solution will lie on the boundary of the feasible region where the isoquant intersects with the boundary of the feasible region, which is right here. That would be my optimal solution. So I could look up these values where x2 is 6 and x1 is 10. Okay, so if you look at this value right here, so if I try to draw the point out at this point, what's happening at this point? At this point, x1 value is 6. Sorry, x2 value is 6 and x1 value is 10. And if you plug those in, you'll get 42 miles. Now you can maintain more miles of road if you go to the straight line over here. If you draw a straight line which is parallel to those lines over here, you could maintain more road, but your constraints are violated in this line, the line that I just drew. Your constraints have been violated. So this won't work at all, right? So the only line where it works is this one, where you're meeting all the constraints and you're still maximizing the amount of roadway that you're maintaining. So how many miles of roadway are you maintaining? You're maintaining, because your x1 value here is 10 and x2 is 6. You can figure this out. So the value that you're maintaining, the road that you're maintaining, it's 3 times 10 plus 2 times 6 equal to 42 miles per day. Does that make sense? Any questions about this? So your answer to this optimization problem is that the maximum amount of road that you can maintain is 42 miles by using 10 units of technology 1 and 6 units of technology 2. And still be able to meet all your constraints. Any questions about this? Are there any questions? Please remember, there are no bad questions. Only bad questions are the ones you don't ask. So please feel free to ask any questions, any doubt that you might have. No questions? Okay, so that's good. Clear all drawings. Move on to the next slide. Okay. So here is the story about the linear programming example. The optimum is always at the corner of the feasible region, as we saw. Or it could be multiple adjacent corners, that's fine. In this case, by coincidence, the optimal solution provides integer values of x1 and x2. That may not always be the case. One way of quickly finding the solution is you can pick any corner of the feasible region. So if you go back to the previous slide, you could start checking these individual corners. You could start checking these individual corners. So this corner, this corner, this one right here, this one right here, or this one right here. And you can figure out where the value of the objective function is maximized. And that becomes your solution to the linear programming problem. Okay. So this is one quick way of finding the problem. This is what we call the simplex algorithm. It's a classic linear programming solution method. And you can also implement these constraints and these objective functions in Excel. And I will post a video that I recorded previously that helps you do that. Okay. So how do we sort of program this in Excel and use a sort of add-on in Excel called Solver to solve that problem? It will be shown to you via a YouTube video. I'll add that to our lecture videos, and you can watch it on YouTube as well. Okay. So now what I want to do is I want to look at a little bit of the mathematics of it, because that way we can sort of do this problem and sort of get into the transportation problem that I'm interested in, the logistics problem, where you have to ship the goods and you want to minimize the cost of shipping. Okay, so here is what I'm doing. I'm considering the standard linear programming formulation, and I'm trying to maximize z as a function of c1 x1 plus c2 x2 plus cn xn. Okay. So these c1, c2, c3 are my coefficient on x1, x2, xn. And then I have these bunch of these constraints, and all of these constraints look like this. If I'm maximizing, all of my constraints look like less than or equal to a11 x1 plus a12 x2 plus a1n xn less than or equal to b1. And how many constraints are out there? There are m total constraints, m as in Mary total constraints. Okay. And then x1, x2, and x3 and xn are my n decision variables. Okay. So here what I have is m constraints and n decision variables. So n things that I can change, and I'm given m conditions that I must meet as I solve this problem. And by definition, in linear programming problems, all my x's have to be more than 0. Okay. Now you'll have to recall a little bit of the matrix algebra. So hopefully you can recall that. Hopefully you can recall the matrix algebra a little bit. So how do you, in particular, I want you to revise how you multiply matrices, how you multiply row vector and column vector and so forth. And I might give you a little bit of the lowdown on it, but if you don't recall it, make sure that you revise it somewhere. Maybe I'll even post or I'll give you a link to the YouTube video that talks about the basics of matrix multiplication. Because being able to write this in a matrix notation is very important, because that's when you can create what we call the primal and dual problems. Okay, and they are very interesting interpretation of the linear programming problem, and that's very important for us. Okay, so let's think about this a little bit. I can write this in the form of a matrix notation. Where I'm trying to maximize Z, which is C times X, where C is a 1 cross n row vector. Okay, so very important to note here. C is a 1 cross n row vector. X is n cross 1 column vector. Okay, so if you recall from your matrix manipulation class or whatever you took, maybe some math class earlier that you might have taken, if you have a 1 cross n matrix, it can only be multiplied by n cross something matrix, because the number of columns, so when I say 1 cross n, that means, first of all, the first quantity represents 1 is the number of rows, n is the number of columns. Okay, so the quantity that appears first, it's the number of rows, and then the quantity that appears second is the number of columns. So in X, what I'm asking you is, what in X, in the matrix X, what is the number of rows? What is the number of rows in the matrix X? It's an n cross 1 matrix. It's an n cross 1 matrix. What is the number of rows in X? What is the number of rows in X matrix? So that's right. Anytime you say it's an m cross n matrix, the first quantity m will represent the number of rows. The second quantity n will represent number of columns. Okay, so in X, even though I'm calling it a vector, the general term will be matrix. Okay, if you have one of the dimension reduced to just 1, then we call it a vector. Okay, if both dimensions are more than 1, then we call it a matrix. But if one of the dimensions is just 1, we call it 1. If it has 1 column, it's called column vector. If it only has 1 row, it's called row vector. And so when I talk about C, it has 1 row and n columns, and X has n rows and 1 column. And then this is the rule about the matrix multiplication, is that if you're trying to multiply 2 matrices, the multiplication is only possible, it is only possible when the number of rows in the first matrix is, number of columns in the first matrix is equal to the number of rows in the second matrix. Otherwise, it's not possible. So when you're trying to multiply matrices, you write them 2 side by side. So you write the dimensions of each matrix side by side, which I'm going to do here. So I'm going to write 1 cross n. So the first matrix is 1 cross n, the C matrix. The second matrix is n cross 1. I write them side by side, and these numbers, this n and this n, has to match. Okay, so this n and this n has to be the same. If these 2 quantities are not same, those matrices cannot be multiplied. Okay, and then if they are in fact the same, it can also tell you the dimension of the resulting matrix, will be 1 cross 1. Okay, if both rows and columns are 1, that means it's just a scalar. There's no matrix, there's no arrays, it's just 1 cross 1. So you can also find out by using the dimension of the resulting matrix will be 1 cross 1. So I'm going to give you a quick question about this. Okay, so if you're multiplying a matrix of these dimensions, I'm going to give you some dimensions here. My question is, if you're multiplying a matrix 3 cross 2 with 4 cross 3, okay, so I'm multiply matrix 3 cross 2 with dimension 3 cross 2 with 4 cross 3. My first question is that even possible? Is that possible? It's not possible. That's exactly right, because this 2 doesn't match with this 4. This 2 doesn't match with this 4. Okay, that means the multiplication is not possible. Okay, so I'm going to give you another example. So if I have a 3 cross 2 matrix, if I want to multiply it with any matrix, the column number has to be 2. So if I multiply a 3 cross 2 with 2 cross 1, now the multiplication is possible because this 2 matches with this 2. Okay, so that's the good news. The multiplication is possible. And then what is going to be the dimensions of the resulting matrix? It's going to be it's going to be 3 cross 1. Okay, the resulting matrix be 3 cross 1. Okay, the resulting matrix would be 3 cross 1. Make sense? Okay, so when I multiply C and X, now I'll kind of go back to this problem here, where C is an n cross 1 row vector and X is n cross 1 column vector. What happens when you multiply C and X together? What dimension do you get? Go ahead and type it up in chat. What dimension would you get when you multiply C? When you multiply C with X? When you do C times X, like I'm doing here, what dimension do you get? 1 cross 1, right? You get 1 cross 1 because n and n are the same, and the resulting dimension will be 1 cross 1. That means you're just going to get scalar. Scalar means a single quantity, and that's what you're trying to maximize. So that means essentially the dimension of Z are 1 cross 1. Dimensions of Z are 1 cross 1. Okay. Such that AX is always less than or equal to B. Now, these constraints is capital A, capital X, and capital B. So anytime I write something capital, that means it's a matrix. A is an m cross n matrix, B is an m cross 1 matrix. Can I multiply A and B together? Can I multiply A and B matrices together in this example? A is m cross n matrix, B is m cross 1 matrix. Can I multiply and obtain a matrix multiplication A cross B? Yes, A cross B is not possible. That is correct. A cross B is not possible because the dimension n doesn't match with this m. Okay, so not possible. A cross B is not possible. Is A times X possible? Is it possible to multiply A times X matrices? A times X, okay? So I'm trying to get A times X, where A is m cross n, and X is n cross 1. So I see some answers in the chat. Yes, that is possible. That is correct. So I can put this. So because this n and this n matches, and when I multiply A and X together, I will get a matrix that is M cross 1 in the final dimension. Okay, and less than or equal to B. So if you're writing an inequality, both sides of the inequality or equation have to have the same dimension, obviously. So if I multiply A and X together, A times X, I should get less than or equal to capital B, where capital B is M cross 1 column vector. Okay, M cross 1 column vector, which is obviously also the dimension of A times X. Okay. And the 0, this 0 is an N cross 1 column vector of all zeros, because I want all of these X's to be greater than 0. Okay. So now what we'll do is we'll try to remember this matrix notation and try to write our original problem and all these constraints that we had in the matrix notation. Okay, so let's try to write a matrix notation for the optimization problem that we just solved. Okay. And then we'll come back to this dual problem in a second. So this is what the roadway example dimension problem will look like. My X will be X1, X2. So I'm going to try to write this. Let's try to take a screenshot of this. And I'll go back to my Google Doc. So based on all the constraints that you're seeing, you're going to see here, I could delete this now because I have the information that I need. So remember, according to my formula here, my equations I'm trying to maximize Z equal to C times X. So I'm trying to write what my C and X's look like. So my X will look like X1 and X2. Remember, it's a column vector, so it's only have one column. My C will look like a row vector. That is the coefficient of, in the objective function, what are the coefficient of X1 and X2 respectively. So when I multiply C with X, and you have to learn how to multiply matrices, and I'm not going to talk about that here. You should know this, but if I'll post a video for it if you need a refresher. But when I do multiply C and X together, I get 3x1 plus 2x2, a 1 cross 1, a scalar. Okay, such that all of my constraints, and all of my constraints are x1 plus x2 greater than or equal to 6, 6x1 plus 15x2 less than or equal to 150. Okay, so I'm trying to basically define A and B such that when I do A times X, when I do matrix A times matrix X, when I multiply matrix A with matrix X, what would I end up with? I end up with left-hand side of all of my constraints. So this will give me, when I multiply this with X, I'll get 6 times X1 plus 15 times X2 less than or equal to 150. So I'm trying to recreate this equation right here, AX less than or equal to B. So my matrix A should look like this for that. And my matrix B should look like this. So I can get A times X is less than or equal to B. And you could see each of these individual lines or individual rows will give me one equation. This gives me a second equation. This gives me the third equation. This gives me the fourth equation. And this gives me the fifth equation. Now, all of these equations sort of look familiar, right? Plus 6 and plus 15 less than or equal to 150. Plus 2x1 plus 3x2 less than or equal to 40. That's one right here. Okay. So they all look familiar. 2x1 less than or equal to 30. That's the next one over. Right? x1 less than or equal to 10 is right here as well. But what about this one? I'm wondering what's going on with this equation. What's going on with this equation? I don't recall any equation with -1 coefficient and -6 on the other side. Which one is that? What equation is that? Which equation is -1 with these coefficients? So even if I write it out, it's -x1, -x2 less than or equal to 6. So I'm trying to sort of give it this format right here on your left. But which equation is this? Did we ever write an equation like this? Think about it for a second. So yes, I finally have a response, because if you recall, all the constraints were basically, you cannot have more than these laborers. You cannot have more than this pickup. You cannot have more than this grader, or you cannot have more than this roller, this number of rollers. But for the supervisor, the constraint was flipped. The constraint was you must have at least 6 supervisor. So the constraint was x1 plus x2 must be greater than or equal to 6. Okay. And if that is the case, I want to be able to write my equation, because if I'm going to do a matrix notation, my sign cannot change. This sign has to be the same for all constraints. So I need to flip the sign of this inequality right here. And how do you flip the sign of an inequality? Remember, in an equation, if you multiply both sides by any number, it remains the same. The number could be positive or negative, it doesn't matter, right? But if you're talking about an inequality and you multiply that by a negative number, the sign flips. So that's exactly what I'm doing here, because I want to flip the sign, all the inequality to have a consistent sign. I wanted to have it a negative less than or equal to sign, but it had a greater than or equal to sign. I multiplied both sides of this equation with -1. So what I'm doing here is I'm going to rewrite this constraint with a greater than or equal to sign, okay, with a less than or equal to sign. And instead of doing anything else to it, I'm going to multiply both sides with -1. Remember, if in an inequality, if you multiply both sides by -1, the sign flips. Or any negative number, really. If you multiply or divide by a negative number in an inequality, the sign on an inequality flips. And that's the flip that I'm trying to achieve here with these negative signs. So does it make sense that what I've written for the matrix C, for matrix A, B, and X, all these numbers, do they make sense now? Any questions about this? Based on what you know from this slide, does this make sense? The value of X matrix, C matrix, A matrix, and B matrix per the slide for our road maintenance problem. So given, are these matrices representing are they going to represent my objective function and my constraints correctly, is the question, based on what you know from the primal problem. Based on what I'm highlighting on the slide, Do these definitions of different matrices make sense? Take a minute. If any question comes up, let me know. Okay, so it looks like it makes sense to you all. So now that we are able to express our problem in the form of a matrix notation, we should be able to write what we call the corresponding dual problem. Okay, so dual problem, you can think of it as a mirror image of the original problem. Okay, how do we write the dual problem? So let's go back to slides here. The corresponding dual problem, if you know values of A, B, and C, okay, so remember the dual problem is also a linear programming optimization problem. And so it will have to have the decision variables. It would have to have constraints as well. Okay, so it will have decision variables. It will have the constraints. And it's a flipped problem in that if your original problem was maximized, now I'm going to highlight the key differences here. This used to be maximized in my primal problem. Okay. My decision variables used to be X. Now my decision variables are W. Okay. And I'm still trying to minimize a value for Y. So I have new objective function now that I'm trying to minimize. And that is equal to B transpose W. And remember, we know the definition of B, right? We know the definition of matrix B from our original problem. And then my constraints will look like this. A transpose W would be greater than or equal to C transpose. And then when I say C transpose, the transpose is the transpose of the matrix. Okay, so transpose means you write the rows as columns and columns as rows. So if you transpose any matrix, you basically transpose it by converting its rows into columns and columns into rows. Okay, so let's try to think about this and how this plays into how would this work? What would the dual problem look like? Okay, so if I know that my A, B, C, and X look like this, if my X, C, A, and B looks like this, they look like this, and I want to write the dual problem, so what I'll do for that is that I will go back to this definition right here, and I will sort of arrange it with this. Can I find a minimize Y B transpose W? So if you know the B matrix, can you write the B transpose? So why don't you guys write the B transpose in a paper and see if that makes sense. Can you write B transpose? Because your dual problem will be minimize Y, which will be B transpose times W. So first of all, let's write down B transpose. So B transpose in this example So I'm trying to write B transpose. And And remember, my B is nothing but the values that I saw here. So my B looks like this: 150, 40, 30, 10, and -6. So my B transpose will look like it will be a, so it's B has right now, it has 1, 2, 3, 4, 5 rows and 1 column. So B transpose will have 1 row and 5 columns. And then this is what it will look like. And see if that makes sense to you. 150, 40, 30, 10, and -6. That makes sense? I can increase the font size. Okay. This is what my B transpose would look like. Next thing I need, if I go back to my slide, I need W. We don't know what W is, but can you tell me what the dimensions of W would have to be? Because remember, I have to multiply the W. W are my decision variables for the new problem. Okay, what would be, the question for you is, because I'm multiplying B transpose with the matrix W, you should be able, and I should get one scalar to minimize, because I know the dimension of Y will be one scalar, because that's what my objective function is, just single dimensional. So you should be able to tell me what have to be the dimensions of W so that I can multiply that by B transpose and be able to get an answer that's a scalar. That's a one by one matrix. So what would be the dimensions? What will be the dimensions of the matrix W? In this example only, okay? So B transpose dimension is, what is the dimension for B transpose? It's 1 row and 5 columns, right? It's 1 cross 5. So B will have what dimensions? Yeah, I see some answers already in the chat. That's good. 5, not 6 cross 1, but 5 cross 1. Okay, 5 cross 1, because it's 1, 2, 3, 4, 5. So it's 1 cross 5. It has to be 5 cross 1 so that I can multiply B transpose with W. B will have dimensions 5 times 1, and W, I'm telling you, are the decision variables for my new problem that I'm trying to write, the dual problem that I'm trying to write. That means my W will look something like this, okay? It will be W1. If I can write this as, my 1 will be like a superscript or subscript rather. Okay, and they won't all be W1, obviously. They're going to be 2, 3, 4, and 5. So this will be your dimensions, where I'm going to say, okay, so these are, and I'll talk to you about why we are learning to do the dual problem. It's a very interesting question. So I'll get to that point. But first we have to learn how to do it, okay? So once we can do it, then we can explain what's the point of this, okay? So can you trust me on this and try to, so this is what my W will look like. W1, W2, W3, W4, and W5. And my constraints are going to be A transpose W would be greater than or equal to C transpose. And we know what C and B look like for us, right? So we know exactly what our C matrix look like. So I'm going to try to copy paste that here. So we know what my C looks like. So A transpose W greater than or equal to C transpose. Okay, what does the C transpose look like? C transpose will look like something like this. Okay, it'll be one gigantic sort of square bracket. It'll have 3, and then below that it'll have the 2, So it's the transpose of this essentially. Okay. And then A transpose W, my A transpose will be transpose of this. So the matrix will look like, I don't know if it'll let me write. So I'm going to just write it without the 6, 2, 2, 1, -1, and 15, 3, 0, 0, -1. Okay, so this is what A transpose will look like. What's the dimensions of A transpose? It has 2 rows and 5 columns. So it's A transpose is 2 cross 5. So if I want to multiply that by W, it has to be 5 cross 1. W is 5 cross 1. So I can, in fact, multiply A transpose with W. So you can see it. Because remember, I want to multiply A transpose with W. So A transpose is 2 cross 5. And W is 5 cross 1. And when I multiply the two, I should get a matrix in 2 cross 1. 2 cross 1. So 2 rows and 1 column. And C transpose. Does C transpose have that dimension? C transpose. What does C transpose look like? My C transpose will look something like this. It'll be 3 and 2. Okay. So this is what my C transpose will look like. Make sense? Questions about this? Okay. So when I do this matrix multiplication, where I rewrite the problem, minimize Y equal to B transpose W such that A transpose W greater than or equal to CT, W greater than 0. And now I've written out what my CT looks like and what my AT looks like. Oops. My AT looks like, and I want to subscript this. Okay. AT is 2 cross 5 matrix, right? Right here. This is my AT. This is your AT. And then this is my CT. Okay, so I got AT and CT figured out. Now, if I know AT and CT, you're ready to write your dual problem, and dual problem will look like this. B transpose W, minimize Y such that B transpose W. So your B transpose W is right here. So if you want to write that down, the way to get it done is, so I'm going to write that down over here, copy paste it. So now let's go back and take a look at, is this what it gives it? If I multiply B transpose with W, 150, 40, 30, 10, and -6. Oh, W will have dimension of 5 cross 1. So my W is not correctly written, by the way. Does that make sense? Is my W correctly written? No, it's not correctly written because it has 5 rows and 1 column. So I should be writing W in vertical way. Okay, because it's a column vector. It's a column vector. So I should be writing B transpose times W. It'll be 5 cross 1. So I should have 5 rows and not. So what I've written here is W transpose, really. Okay, so I should be writing this as, it'll be W1, W2, W3, W4, and W5. So this is what it'll look like, okay? And then obviously these will be subscripts. Okay, so when I do B transpose times W, I'll get this. 150 W1 plus 40 W2 plus 30 W3 plus 10 W4 minus 6 W5, such that how many constraints would this problem have? This will have 2 constraints because I'm trying to write A transpose times W. So A transpose is 2 cross 5. And W is 5 cross 1. So I'll get a 2 cross 1 constraint. So I'll get 2 constraints. Okay. So it'll be 6 times W1, 2 times W2, this 2 times W3, this 1 times W4 minus W5, and then 15 times W1, 3 times W2, nothing for W3 and W4, and minus W5 greater than or equal to 2. Okay. So what you can see here is that when you write the dual problem, your constraints, your number of constraints become your number of decision variables. So I had 5 constraints in the original problem, and they became 5 decision variables for the dual problem. So 5 constraints in the original primal problem became 5 decision variables in the dual problem. And I had 2 decision variables, x1 and x2, if you recall. And that became my number of constraints in the dual problem. Okay. And if you actually solve this problem, you still get y star being 42. Okay. Y star being 42. And if you want to write what W transpose will look like, W transpose will look like this: 0.133, 0, 0, 2.2, and 0. And this is very interesting because if you look at that solution for the dual problem and solution for the primal problem, so you're trying to minimize the y, and the minimum value of y will still come out to be 42. So the primal problem and the dual problem have the exact same solution, have always the exact same solution. Even though you're minimizing the y and you are maximizing the z, in the original problem, you're maximizing it. Now in the dual problem, you're minimizing it. The number comes out exactly the same, 42, right? Because that's the number we got earlier. And then if you solve this, you will see that among the decision variables, three of the values are 0. So W2, W3, and W5 have 0 value at the optimal case. And WT is 0.133 and 2.2 value for W1 and W4. Now, how we solve it, I just showed you one example of solving it, and you'll learn to solve it in Excel as well. But for now, let's assume that this is in fact the answer. It's a very interesting answer because what it's telling you is that in your original problem, you had 5 constraints. 3 of those constraints did not matter. 3 of those constraints did not matter because if you look at the solution of the dual problem corresponding to those constraints, W2, W3, and W5, they have the value 0. And this is what we call the shadow price. That means even if you relax those constraints, if you relax the second constraint of the original problem, third constraint of the original problem, and the 5th constraint of the original problem, it would not change a thing. You won't be able to maintain any more rows. Your first constraint was about the workers. So that means if you add one more worker, you'll be able to maintain 0.1333 additional miles of road. Okay. And if you're able to add one more grader, you'll be able to maintain 2.2 additional miles of the road. So if you look at the constraints or the solution to the dual problem, that tells you shadow price for each of the constraints that you had in the original problem. So I'm going to repeat it again. If you look at the solution of the dual problem, that tells you the shadow price for each of the constraints in the original primal problem. That means if you look at this solution, 0.133, that means if you add one more worker, you'll be able to maintain 42.1333 miles of road total per day. And that's 0.133 miles extra. So if you add one more grader, you will be able to maintain 44.2 miles of road. Okay, so 0.133 more miles per day, 2.2 more miles per day. So dual problem solutions tell you what the shadow price for each of the original constraints would be. Okay. Now, I'm going to stop here, but in the next class, we'll pick up this discussion, but in the context of the transportation problem, where you have M origins and destinations, M origins that have to produce, each is able to produce output SI, and destination that is each able to receive dimension, each needs to receive quantities dj, and the cost of transporting from point I to point J is Cij, and you want to minimize the Cij, which is the total cost of shipping products from origins to destination. Okay, so what we'll do is in the next class, we'll pick up the transportation problem topic, and then we'll talk about the primal and the dual problem and what are some of the interpretations of it. Okay, I'll stop right here. And unless there are any questions, I'll see you guys at 8:10 tomorrow morning. Thank you, guys. And remember to review matrix algebra a little bit so that it's easier to understand this aspects of the optimization problem. Thank you.
Thank you.